Ladies and gentlemen, Kip Thorne. He doesn't need any introduction.
Thank you. That's the best introduction I've had in a long time. Let me just now, there we go. Okay. At the beginning of COVID in 2020, March 2020, I gathered together a group of colleagues who had worked very hard on LIGO over a long period of time, and we agreed that we would try to write a detailed history of LIGO that went into all aspects of LIGO, and something that would be both interesting for people of this generation, but also a resource for future generations. The people involved were Ray Weiss, Barry Barish, myself, Peter Fritschel, Peter Shawn, Stan Whitcomb, and Kim Burtnick is our superb editor. We've been working on this now for 5 years. We have about 1 more year to go. But I've learned an enormous amount in the process of this through interviews of lots of people and the work that each of us have done, putting things together and comments from many people. And so what I will say today relies very much on that. Let me begin with 1972 to 79, when the seeds for LIGO were being laid. This was the early era of relativistic astrophysics. Black holes, neutron stars, the Big Bang were being studied observationally through the recently discovered quasars, pulsars, X-ray binaries, cosmic microwave background. And I had arrived at Caltech 6 years earlier and had built a research group of 6 graduate students, 4 postdocs, and lots of visitors working on these things, and also on the issue of what could you do with gravitational wave astronomy if it could be created. It was then that I received from Ray Weiss a technical paper that he had written and published in an internal progress report series at MIT. He didn't publish it in a journal because he figured he shouldn't publish until after he'd built one of these gravity wave interferometers and maybe it had seen gravitational waves. That was Ray. And he proposed then gravity wave interferometers of a delay line sort in which you had 2 mirrors that hung from overhead supports were looking down on them. The gravitational waves, of course, push these mirrors apart while pushing those mirrors together on orthogonal arms. And then that stretch and squeeze oscillated, and the laser beam was used to monitor those oscillations through sending the beam through a beam splitter and through a hole in this mirror, bouncing back and forth and making many spots within this cavity, coming back through that hole and recombining at the beam splitter, and of course producing a rising and falling intensity proportional to the stretch and squeeze in the 2 arms. I looked at this idea, I looked at the numbers, and I was just at the verge of sending to the publisher the manuscript for a classic textbook called Gravitation that I'd written with Charles Misner and John Wheeler. And I wrote in there my honest view of this, that this was not at all promising. And why did I think it was not at all promising? Well, for success, one needed to see a gravitational wave, one needed to be able to measure motions of the mirrors at the level of about 10 to the minus 18 meters, or if you had arm lengths that were about a kilometer or a few kilometers. And this is basically based on what we knew of the strength of sources at the time, which we were pretty much right on, corresponding to a strain of about 10 to the minus 21. What one had in terms of technology was an ability to measure changes, motions of the mirrors at the 10 to the minus 12 meter level. So that was 1 million times less than what was required, but over just 1 meter. So that was another factor of 1,000. You need to increase that 1 meter to 1,000 meters. So we could measure strains of 10 to the minus 12. What was needed was 1 million times lower displacement noise and 1 billion times lower strain noise. And that just looked totally ridiculous to me. And to everybody else who looked in from the outside on review committees and so forth, and astronomers. But I just didn't believe that was possible until I spent the period 73 to 76 in conversation occasionally with Ray Weiss, with Vladimir Brzezinski in Moscow. I studied Ray Weiss's 1972 paper in depth, and gradually I became convinced that this had a real shot at succeeding, and that I should devote a large portion of my career and that of my students to trying to help the experimenters pull it off if they decided to move forward. When I look back in retrospect at Ray's 1972 paper, and I really see the detailed analysis that he did of all the noise sources and how you might deal with them and what you could achieve, I see it as the most prescient, but also the most powerful, the most interesting, really the most important paper that was ever written in this field. And when I look back in his contributions to LIGO, working on essentially all aspects of LIGO in the laboratory, doing theoretical calculations as well. He was a good theorist as well as an experimenter. I do regard him as being the dominant, most important, the most person within the effort who really made by far the biggest contributions. Just enormous respect for him. So today we should be celebrating Ray Weiss and his contributions. In November 1976, then, based on my finally coming to understand this, I submitted a proposal to Caltech to create a research group working in gravity wave detection and experimental gravity. I gave this to Martin Schmidt, the chair of the Physics, Math, and Astronomy Division, and he appointed a faculty committee to study the proposal that included Barry Barish, Alan Moffat, the leader of radio astronomy, Gary Neugebauer and Tom Tombrello, who would become division chairs soon after Martin Schmidt and myself. And we spent 2 years studying the field, interviewing the leaders who were working in the field, doing calculations of our own. And we ultimately came to a decision, yes, and this was ratified by the PMA faculty and the Caltech administration. Yes, we should move forward, and we should bring Ron Drever from Glasgow, Scotland, to lead it. Now, why Drever? Because we felt that it was so difficult that we had to have somebody with enormous creativity, because they were going to need lots of creative ideas in order to really pull this off, and this was really a characteristic of Ron. He heard just the names of things that he invented or was co-inventor of. Fabry-Perot arms, PDH locking, power recycling, signal recycling, all of which are major parts of LIGO today. And the Fabry-Perot arms, he pushed very hard that what one should do, instead of having a delay line interferometer where the light is bouncing back and forth, making discrete spots, you should have the separation between these mirrors be a half-integral number of wavelengths, so the light will resonate inside these arms. And and it would build up to high intensity and then leak back out and interfere at the photodetector. And this scheme, very, very hard to make work successfully. Nevertheless, if it could be made to work and work really reliably, would have very high versatility. So today we should be celebrating Ron Drever along with Ray Weiss for his creative contributions to LIGO. The funding for gravity wave interferometers, the story about this is that in 1979, Caltech, having made the decision to move forward, invested approximately $2 million of Caltech's funds to get their effort off the ground. That inflates to about $14 million of Caltech's own funds today. And that was absolutely incredible. By contrast, NSF had given Ray $53,000 in 1975 and nothing after that. MIT had given him nothing, and he couldn't find a single person on the faculty at MIT who would give him any encouragement even, or on the administration. And he remained bitter about that about how he was treated in the early years, up until he died very sadly about a month or two ago. In 1979, NSF, seeing what Caltech had done, carried out a similar kind of a study, much quicker than Caltech's, but a similar kind of a study, and came to the same conclusion as Caltech had done and began providing significant funding to Ray and to Ron Drever at Caltech. And so we should be celebrating today Caltech's PMA faculty and administration of that era, including the acting president, Robert Christie, and at that time, the new president, Marvin Goldberger, who committed this $2 million to moving forward and shook things up everywhere else and got everybody else's attention and started moving forward at NSF. The era in 1970s to 1986 was an era in which there were 4 research groups working in parallel, partly collaborating, partly competing on perfecting this gravity wave interferometers through building prototypes. These groups, by 1986, had improved the interferometer displacement noise by a factor of 1,000. So at least logarithmically, they were halfway to the needed 1 million. And as we will see, that turned out to be enough to justify moving to the kilometer scale and getting the other factor of 1,000 in a kilometer scale interferometers. And so this was absolutely crucial, and it was a great achievement. MIT was the first group, 72 to 86, with a 1.5 meter prototype of a delay line sort that Ray Weiss and his group built. And, but more importantly, at MIT, Ray and his group carried out a feasibility study for kilometer scale interferometers that really became the handbook for moving forward toward kilometer scale for the following decade. And that had an enormous impact. So we should be celebrating the MIT gravity wave group of that era, 1972 to 1986. This is a list of the people who were in the group in that era, and I have circled some that you'll know who are still very active and have played a huge role, but Ray Weiss, Peter Fritschel, Peter Salson, David Shoemaker. The Max Planck Institute, so originally in Munich, there's a group that built a 3 meter prototype of with the delay line arms. And then they moved to Garching nearby and built a 30 meter prototype. This group was led by Heinz Billing. It was a group of very mature scientists, very different from the other groups. The other groups were primarily postdocs and graduate students. This was a group of very mature scientists who had begun by building computers. They had switched over and built bar detectors of the Joe Weber type, and then they switched and built interferometers. And so they had a lot more money to work with because of the nature of the Max Planck Society. With this superb skills of this group, they basically were leading everybody else in sensitivity, though the other groups pretty much caught up by about 1986. I note that David Shoemaker was in that group for 2 years. He went from MIT to Germany, and that provided a lot of cross-fertilization between Ray's group and the Max Planck group. Sorry. And so we should be celebrating the Max Planck group, which contributed so much in this early R&D effort era. Glasgow, 1976, they began working on interferometers under Ron Drever's leadership and the leadership of Jim Huff, who was the other professor in that group. They, as I indicated, they built an interferometer prototype with Fabry-Perot arms, a 10-meter prototype. And this is a list of the people. Actually, I have the list from 76 to 97 when they joined the LSC, the LIGO Scientific Collaboration. That's just the list I happen to have. But you'll see here the names of particular people that many of you will know today, know their huge contributions that they made. And finally, Caltech. We brought Stan Whitcomb from the University of Chicago as an assistant professor to work with Ron Drever. Ron Drever was commuting back and forth between Glasgow and Caltech in that era. And it was really Stan who was the hands-on leader of this effort in building this 40-meter prototype and getting things going. Stan went on over the coming years to be deputy director of LIGO to be acting director on occasion, but also to be really, in some sense, a chief scientist of LIGO, if there was a chief scientist in those eras leading up to the big detection. And I think Stan Whitcomb, to my mind, really, it was the experimenter after Ray Weiss that I most respected in that entire period. So we really should be celebrating the Caltech gravity wave group of that era, 79 to 86. Here are a list of a few people that you may be familiar with, and particularly, along with Ron Drever, Stan Whitcomb. 1984, the LIGO collaboration was created in a very interesting way. It began with pressure from the National Science Foundation. Marcel Bardon and Richard Isaacson. Marcel was the head of physics. Richard Isaacson was the head of gravitational physics. And they understood very clearly that in order to have adequate manpower and a range of skills to pull this off, and in order to get the money from Washington, it was absolutely essential that Caltech and MIT collaborate. And so they put the pressure on. And at Caltech and MIT, there was this troika trying to lead the effort as we began to try to collaborate of Ray Weiss, Ron Drever, and myself. Ray and I said, of course, collaborate. And Ron resisted as hard as he could collaboration. Why? Because Ron, just by his character of his personality, he really needed to be in complete control of everything that he was working on in order to work very effectively. And if he wasn't in complete control, he would lose his enthusiasm and he would lose his ability to work. And it was just a simple characteristic of his personality. And it really couldn't be changed. So he resisted. At Caltech, Ed Stone was enthusiastic about collaboration. At MIT, Ed Stone was the head of PNMA at the time. John Deutsch, who was the dean of science and then became the provost and had the huge clout, not interested at all. Nor was anyone else at MIT except Ray Weiss. So this was a parent prescription for dysfunction. But in fact, much was in fact accomplished in that period from 84 to 86, including achieving in the 40-meter prototype, the necessary sensitivity to move forward toward the kilometer scale interferometers. But it was Bardon and Isaacson who in that era and moving on into the next decade or so really were superb in giving advice to us and in choosing review committees that would review things in a very hard-nosed way that really made things happen from the Washington end. And so I would like to really be celebrating Marcel Bardon and Richard Isaacson at NSF. I won't say anything else about other people at NSF for lack of time, but there certainly were others as the years wore on. In 1996, Richard Garwin, perhaps the most influential physicist, most influential with Congress and with NSF, most influential throughout Washington, he wrote a letter to Marcel Bardon that I am quoting here. I am firmly of the view that we do not need right now to spend $40 million or $100 million on LIGO. This is the sort of the kind of thing we are now talking about, informally talking to NSF about. If there is such an interest, then I think it would be useful to have a 2-week summer study when people not involved in the experiment have a chance to contribute. So Bardon had a natural response. He had Ray take the lead in organizing this, but it turned into a 1-week in-depth study in November rather than a summer study. And this is all that he could get the crucial people together for. A study of LIGO's plans and the worldwide gravity wave effort, and a blue ribbon committee to make recommendations to NSF about what to do about LIGO. The blue ribbon committee, you can see here in white the names of the people on the committee. It was a group of experimenters who had enormous prestige, but also enormous understanding and skill, again, in all of the technologies that would underlie LIGO. And Garwin was put on the committee, of course. And Saul Tucholsky was the only person from the relativity or gravity wave community on it. Saul, of course, is a professor here at Caltech now. He is a theorist, but he understood things quite broadly in terms of gravity waves, and so they had their token gravity wave person, but the important people were these others. The Blue Ribbon Committee, after a week-long study, issued a report. It said that there is a high probability of success, that LIGO will produce a giant leap in understanding of gravity and astrophysical phenomena. This is a quote from the report. The committee urges that LIGO's design be completed. This is the conceptual design in technical terms. And its construction then be brought to NSF for consideration and hopefully for funding. They said that it's essential for LIGO to have two sites separated by at least 1,000 kilometers, even though groups in Britain, France, and Germany have plans similar to LIGO, because such a network, including two in the US and those that were being planned in Europe, would be very important for the ultimate scientific payoffs. Now, this is a remarkably accurate blueprint for what actually happened over the subsequent decades. You just look at it, that's what happened. And when gravity waves were discovered, I am told that Richard Garwin took great pride in having triggered this study and having signed off on this report that really was the thing in Washington above everything else that gave us the impetus to move forward. And so we should be celebrating Richard Garwin and the Blue Ribbon Committee today, but also a sequence of subsequent review committees, often shared by Andy Sessler, who had the same character of people who had expertise in all the technologies that were involved and could give NSF advice about how we were doing and give people within LIGO advice about where there might be things that you're missing. But these review committees played an enormous role, both in ensuring continuing funding in Washington and great advice to the people within LIGO. The Blue Ribbon Committee also had in its report some very strong words about the Troika must be replaced by a single scientific project leader. That was music to my ears. And the choice of delay line versus Fabry-Perot arms must be made quickly. And so in response to this, Robbie Vogt was appointed the director of LIGO. He was a Caltech professor. He'd been PI on many space experiments. He was JPL's first chief scientist and defined the job of chief scientist at JPL. And he had been Caltech's provost. And Robbie, I'm going to call him Robbie, even though it says Vogt here a lot. One, because that's the way I think of him, and two, because there's another Vogt who's currently the head of the Office of Management and Budget, that I don't want any confusion between the two. Okay. So Robbie chose the Fabry-Perot arms, even though the prototypes were not operating fully in the way that they were supposed to yet. And it was going to require a few more years until they would. But it was clear that if they could be made to work properly the way they were designed, that they would be very superior. But the choice was not obvious. The delay lines were much more straightforward, and they were certainly going to work properly. In retrospect, it really was a wise choice. Robbie hired 5 engineers. They, together with the physicists, worked together to complete LIGO's conceptual design and to cost it. And Robbie gave preliminary cost of $180 million to NSF director Eric Bloch, who was a friend of his. And there was a big misunderstanding. Bloch gave that $180 million to the Office of Management and Budget as a final total cost. And there was no turning back. It could not be adjusted. So in order to live with that cost, Robbie was forced into a very, very lean management structure and staff. Nothing like the kind of robust structure that one normally has for large projects. and that came back to bite us, as I'll explain in a few minutes. Robbie led the group in writing a superb proposal for LIGO's final engineering design and construction and submitting it to NSF in November of 1989. And it sailed through with tough reviews and was approved by the National Science Board in October of 1990. 1990 was also a red letter year, and the MIT had a new president, Chuck Vest. And Vest was a great supporter of LIGO, and he turned things around at MIT, along with Claude Canizares, the director of the Center for Space Research, and Ernie Moniz, the new chair of physics. And so almost overnight, MIT became a vigorous and enthusiastic partner with Caltech, and has remained so ever since. So we should be celebrating Vest, Canizares, and Moniz for turning MIT around and making this a true two-institution collaboration. Autumn 1991, after a battle with critics, Robbie won congressional funding for LIGO, $23.5 million for FY92. Hanford, Washington, Livingston, Louisiana were chosen as the sites for LIGO's gravity wave interferometers. And Robbie's team developed detailed designs and plans for the initial interferometers, one at each site, and brought the facilities to the verge of beginning of construction. So we really today should be celebrating Robbie Vogt and his LIGO team of 1987 and 1993. This is the Caltech part of the team, and this is the MIT part of the team. In 1993, approximately, it became very clear to me and perhaps to a few other people that there was an absolute necessity for two additional parallel R&D tracks in order for LIGO to succeed. Let me explain this way. The two strongest sources, it was clear by then, for gravity waves for LIGO would be binary black holes and binary neutron stars. Binary black holes are typically 10 times heavier than binary neutron stars, so we see them 10 times farther. So the volume over which the black holes can be seen is 1,000 times greater than for the neutron stars. And it seemed to me that this was very likely to outweigh the rarity of black holes compared to neutron stars in the universe. And that therefore, the first things LIGO would see would likely be black holes. This was not a commonly adopted view, but it was my view at that time. And we will see many more black hole binaries than neutron star binaries, and we would need black hole binary waveforms in order to be able to understand the observed gravitational waves, and therefore, we needed a vigorous new R&D track for computing binary black hole waveforms to be used to underpin data analysis for LIGO. In addition, relying on studies carried out by Sturl Finney here at Caltech and others, I had an estimate of the strongest gravity waves that LIGO will see at this time. And that was that the strains would be between 10 to the minus 20 and 10 to the minus 22, with 10 to the minus 21 as a best guess. But there was a problem. At the level of 10 to the minus 22, or if you were getting anywhere close to it, quantum noise would hide the gravitational waves, quantum noise in the gravity wave detectors. So if I felt it was essential that we have running along a third track of R&D for developing techniques which today are called quantum precision measurement technology, techniques to deal with quantum noise and being able to conquer it, and so that the gravity wave detectors could move forward at that level. So in 1993, both of those tracks became high precision in parallel with LIGO track 1. I'm going to talk to you about track 1 all the way up to the gravity wave discovery. And then I'll say at the end of my talk only a few words about tracks 2 and 3, which, however, were tremendously important. Track 2, crucial for the first detection, and track 3 is tremendously important today. Okay, so back to track 1. 94, there was a transition of leadership. NSF became very concerned about LIGO in the 93 to 94 era, particularly Bob Eisenstein, who had succeeded Bardon as the head of physics. They were very concerned that if they're going to spend hundreds of millions of dollars, you needed to be sure that this would succeed technologically. And that could only be assured if you had a very robust management structure like you have in high energy physics, not a really lean management structure like Robbie had been constrained into by this misunderstanding about the budget. But Robbie, with his constrained budget, could not comply, nor could he convince NSF to increase LIGO's construction budget. So after intense discussions, Caltech President Tom Everhart replaced Robbie as LIGO's PI by Barry Barish, and then Barry negotiated with NSF a sufficiently increased budget to pay for robust management. Basically, NSF had confidence in Barry as a manager for LIGO or a director for LIGO, operating with very robust management as he had done over his career in high energy physics. They didn't have confidence that Robbie could run a robust management, and so they forced this change. Barry had been leader of Caltech's high energy physics experimental program and had served on many LIGO advisory committees, so he was well prepared to step in. But it was really tremendously important that he and Robbie Vogt actually had high respect for each other. So he appointed Robbie as the leader of the group that was designing and setting up to build the first interferometers. And Robbie, many of you may know Robbie. Robbie, it's hard to imagine, but he stepped down from being the director of LIGO to being the leader of the initial interferometer group for 2 years. And that smoothed the transition of leadership between Robbie and Barry in really multiple ways, after which Robbie resigned, left LIGO, and actually went on to become an advisor to the president of the University of California for Los Alamos and other national labs that the University of California manages. But Barry was off and running then. And under Barry's leadership, Barry more or less accepted Robbie's plans for the facilities and initial interferometers after detailed review. Robbie had not thought much beyond the initial interferometers, just didn't have time to. He had his hands full, particularly since he had such a lean management structure. And so Barry thought things through and said, we have to focus on 2 generations of interferometers, initial and advanced. The advanced must have high probability of discovering gravitational waves because if you build the initial ones and then advanced ones and neither of them see gravitational waves, you're dead in Washington. No hope to get more money big money after that. So they've got to see gravitational waves. And many things can go wrong in the advanced interferometers, so they're going to be very complex. The initial interferometers then, in his vision, would reveal pitfalls and teach us how best to design, construct, and install and commission the complex advanced interferometers. And it was essential, he argued, that NSF and Congress be ready to fund the advanced interferometers well before the initial interferometers have reached their design sensitivity. And that was really an approach, a bold approach. He said we have to be bold in order to really succeed. If there's a long delay between the initial interferometers and the advanced interferometers, the cost is just going to go up sky high further, and we may never ever get this done. And that bold approach was absolutely crucial to success. Because of the complexity and also of the advanced interferometers, also data analysis issues which had not begun to be sorted out, Barry planned for far more physicists and engineers than Robbie Vogt had. Robbie had only 40 physicists and engineers when he was replaced by Barry. Barry expanded to hundreds, as you well know, and he did this through setting up the LIGO laboratory and the LIGO scientific collaboration, each with its own responsibilities. And by 2015, the LIGO scientific collaboration had 1,000 members, roughly, at 82 institutions in 16 nations. Just radical change in the structure of LIGO. And under Barry's calming leadership, NSF, which had been quite unhappy with Robbie, became very happy, as did Congress. The construction, installation, commissioning, and operation of initial LIGO interferometers went remarkably well, and it followed Barry's plan, except for a several-year delay due to largely to Washington politics. So we should be celebrating very much so Barry Barish's leadership and the LIGO laboratory, which he set up Caltech, MIT, Hanford, and Livingston. And so I have a roster here I'm going to show you of the people in the Caltech branch of the LIGO laboratory between 94 and 2017, which is when our history of LIGO ends. We basically go up to there and don't go beyond that. But it's quite interesting to see this list. It's a 2-column list, so there are twice as many people there as you might think when you recognize there are 2 columns. But page 1, page 2, page 3, page 4, page 5, page 6, page 7, page 8, page 9, and page 10. That really is a tribute to what a huge number of people have made enormous contributions to this. It was just a very different kind of an operation, and it had to be, and it was so very successful. So we should be celebrating the LIGO laboratories at Caltech and at MIT and at Hanford and Livingston. And in fact, all of the LIGO lab rosters for all 4 sites are works in progress in the LIGO history I'm working on. And I'm asking that members, people who are here who are involved in LIGO or have been, read the rosters that we have put together. These are works in progress. You can read them at that location, https://tinyurl.com, LIGO GW rosters, and provide comments and corrections. The method for providing comments and corrections is being worked out by Kim Burtnick, our editor, and will be described at that location next week. And we'll send this information around to the LIGO Lab members, but we really do want that help from you over the coming months in sorting this out. We should also be celebrating the LSC and its spokespersons, Ray Weiss, Peter Salson, Gabby Gonzalez, David Wrightsey. The LSC has been enormously important in pulling this all off. And so they should be celebrated as well. LIGO in 2006 to 2015. In 2006, the world's high-energy physics community begged Barry to resign as LIGO director and lead a study of the International Linear Collider. With LIGO in good shape, Barry left and J. Marks succeeded him. Initial LIGO saw no gravitational waves, as had been thought likely. And in 2010, there was a smooth transition to installing advanced LIGO. In 2011, J. Marks was succeeded by David Wrightsey, who was just ending a term as LSC spokesman. And again, a very smooth transition. And so Wrightsey has had a wonderful run and had stepped down, I think, only very recently this year. So we really should be celebrating J. Marks, David Wrightsey, and other people who played major roles in LIGO leadership, including Albert Lazzarini, the longtime deputy director, Dennis Coyne, the longtime chief engineer, and a number of others that I don't have space to write down here. But really, the leadership has been superb within the LIGO lab. 2015, the event that we are celebrating. September 14 of 2015, advanced detectors were being tuned in preparation for the first gravity wave search to begin on September 18. An apparent gravity wave signal arrived, and David Wrightsey declared the first search had begun. The data were analyzed with pipelines based on the binary black hole waveforms from the track 2 that I mentioned that was going along in parallel. Those waveforms that we needed were in hand by about 2013. That was the goal, to have them in hand before gravity waves were discovered. And The result was the famous GW150914. By comparing the numerical relativity waveforms from what's called the SXS collaboration with the cleaned up waveforms that were observed, the famous results were inferred that there were two initial black holes that merged with masses of about 29 and 36 solar masses for a total of 65 solar masses. Final black hole of 62 solar masses. 3 solar masses went into gravitational waves, and this was a distance of 1.3 billion light years from Earth. Particularly important was that those simulations, the numerical relativity simulations, not only gave us waveforms, they told us what was happening during the collision. And this is a visualization of what was happening during the collision to produce the waveforms, as seen in our universe. And in order to visualize the warping of space and time around the two black holes, as seen looking down on our universe from a higher dimensional bulk, as we say, a higher dimensional space. And these two funnels down here are the black holes orbiting around each other. And deep down in here, there's a color going to red where time is slowing as you near the horizon of the black hole. And you see the two black holes orbiting around each other. And up here, they're going to collide and merge shortly. And you see a giant splash going on in the shape of space. And then a splash and oscillation in the rate of flow of time down in here as the black holes have merged. And that is what I like to call a storm in the shape of space-time that generates the gravitational waves. But it turns out that that movie, a very famous movie, only captures a modest portion of what's going on in the storm in space-time. There also is worked out by going into the simulations, looking at them very carefully, and then doing some analytical work. Yanbei Chen here at Caltech and his students working together with me figured out that sticking out of these two black holes at the time of the merger are tendencies that stretch and squeeze. A stretching tendex, these blue lines, it stretches outward along the blue lines and squeezes around like that. Coming out of the merger region is a squeezing tendex. It's being squeezed in this direction. It squeezes space in this direction, stretches in that direction. And these tendencies swing back and around as the two black holes go around each other, and they become the gravitational waves that were observed. But there also are, sticking out of the two black holes, this is looking now in from the bulk, you also see vortices of twisting space, counterclockwise vortex and clockwise vortex, due to the spins of these two black holes. So each black hole has a counterclockwise vortex and a clockwise vortex. These vortices of twisting space swing out and around as the two black holes go around each other. And these outflying vortices generate entwined tendencies that stretch and squeeze, as shown here in this painting by my dear friend, the painter Leah Halloran. And those become the gravitational waves that we see. And it's incredible that there's all of this going on that we didn't understand at all until they did the numerical relativity calculations for LIGO, and this came from track 2. So we should be celebrating the people and the teams who contributed to track 2, the binary black hole waveform computation and visualizations, particularly Franz Pretorius, who triggered the breakthroughs in the binary black hole simulations, Saul Tucholsky, the leader of the SXS collaboration, Larry Ketter, Harold Pfeiffer, and Mark Shield, the primary authors of the SXS computer code that did the numerical relativity, and many, many others, as will be spelled out in the history of LIGO. Finally, just a few words, quantum precision measurement. Nature was kind. LIGO discovered gravitational waves at a strain of about 10 to the minus 21 before quantum noise was a problem. But today, because the quantum noise issue was pursued in case it was needed, with sensitivity approaching 10 to the minus 22, we do need the quantum precision measurement today, and we have it. Quantum precision measurement in the form of what's called frequency-dependent squeezing was invented at Caltech by Carlton Caves and Jeff Kimball in the 1980s and 90s. perfected and made robust in 95 to 2020 by the LSC groups of David McClelland in Australia and Roman Schnabel in Germany, and Nurgas Malvavala's group at MIT, and installed into advanced LIGO by Lee McCullough and his colleagues at MIT. And so we should be celebrating Caves, Kimball, McClelland, Schnabel, Malvavala, McCullough, and their colleagues who have given us the quantum precision measurement in the form of what's called frequency-dependent squeezing. And that frequency-dependent squeezing is now operating in LIGO and is in considerable measure responsible for the fact that today we see several black hole collisions each week compared to once every 6 weeks when LIGO first turned on. And as you all know, there is also a Ginsberg Center for Quantum Precision Measurement under construction to be completed next summer, in which second-generation quantum precision measurement techniques and technology will be developed by not just gravity wave people, but people working in other fields with nanotechnology, with optical atomic molecular physics. And so I think I'm tremendously grateful to Caltech for the support that it has given to move forward in these ways. And I thank you very much.